Another product that can come in handy when trying to identify a TVS is spectrum width. In reality, a single radar pixel can contain millions of targets, each with its own velocity. The radar averages the velocities of all the targets within a single pixel to come up with the velocity value for that pixel. Spectrum width is the range of velocities within a single radar pixel. In situations of high atmospheric turbulence, such as within a tornado, targets tend to move in a varied, chaotic fashion. The range of velocities in a given pixel is large, and therefore spectrum width will be enhanced at the location of the TVS. The various targets within the vortex, both meteorological and non-meteorological, have different aerodynamic qualities, yielding a wide range of velocities and high spectrum width. Spectrum width also does well identifying boundaries, especially when they may be shrouded by precipitation in reflectivity data. Prior to the advent of dual polarization radar, meteorologists were unable to confirm whether or not a tornado was in progress solely from radar data. However, because dual polarization radar can analyze the horizontal and vertical characteristics of targets, we can now tell whether or not debris is being lofted by an ongoing tornado. This is manifested in a feature called a tornado debris signature, or TDS. TDSs appear in correlation coefficient data as a small area of lowered correlation coefficient co-located with a tornado vortex signature. Correlation coefficient tells us how similar or correlated the targets are that a radar samples. In a tornado, each piece of lofted debris has different horizontal and vertical characteristics, as well as different orientations. This dissimilarity yields a decrease in correlation coefficient within the tornado. Tornadoes can loft debris quite high into the atmosphere, so a TDS at the lowest elevation angle may also be accompanied by a debris signature at higher altitudes as well.
Join our channel membership and unlock instant access to full-length storm chasing presentations. Click the subscribe button below and then select join, or just click the join button on our profile page.
In fact, if a tornado vortex signature is within 80 miles of a radar site, tornado intensity can be estimated using a combination of rotational velocity and the maximum height of the TDS. As illustrated in this chart, in supercells, weak tornadoes, EF0 to EF1, tend to feature a rotational velocity at or below 40 knots or 46 miles per hour and a maximum TDS height under 8,000 feet above radar level, while violent tornadoes, EF4+, typically have VROTs in excess of 85 knots or 98 miles per hour and maximum TDS heights of over 18,000 feet above radar level. Some of the most intense tornadoes can loft debris over 20, 30, even 40,000 feet above ground. In addition, the rotational velocity thresholds are slightly lower for QLCS tornadoes, and there can be some overlap in VROT and maximum TDS height between weak and strong and violent tornadoes. Again, a TDS must be located in the same spot as a tornado vortex signature, otherwise it's a false alarm. In this example, notice that this area of lowered correlation coefficient does not correspond to a TVS. As a result, this TDS is illegitimate. TDSs are also persistent features. They will not just show up for one scan and then completely disappear in the next. Lofted debris takes time to fall out of the sky, so even after a tornado has dissipated, a debris signature is often present in correlation coefficient data, albeit less concentrated and intense. On the other hand, not all tornadoes produce a TDS. Some tornadoes may not be strong enough to loft debris to the height of the radar beam, or they may traverse areas with very little debris to loft. In these situations, you may not be able to confirm that a tornado is in progress just from radar data, but when a legitimate TDS is present, a tornado is definitely occurring. While correlation coefficient provides the most effective way to see lofted debris via radar, differential reflectivity also has utility in this regard. The random orientation and irregular shape of tornado debris typically yields an area of low differential reflectivity coincident with the tornado vortex signature. In addition, intense, damaging tornadoes can exhibit a reflectivity feature called a debris ball. This is a small area of enhanced reflectivity coincident with the TVS at the tip of a supercell's hook echo. The large size and concentration of lofted debris in and around a tornado returns an increased amount of energy to the radar, which yields enhanced reflectivity. On rare occasion, very little precipitation may wrap around a supercell's mesocyclone, creating what's called a low reflectivity hook echo. In this case, the first sign of a tornado may be a debris ball that appears to be detached from the parent supercell.
Remember to check out those links in the description below, and then watch another video.